Hello guys, welcome to another episode of COVID Chemistry. We're going to be looking at part 2 of the chemical changes. We had a little bit of homework we wanted to do and review some more quite advanced content in terms of these chemical changes. So yesterday I wanted you to be able to identify a strong acid, a weak acid, a weak alkali, a strong alkali, then identify the dissociation equations relating to this. So let's have a nice recap. Hopefully you have your work in front of you now to work through this together with me. So, strong acid, very, very popular within schools and in all chemistry classes, hydrochloric acid. Always referenced to in many exams when we're looking at a strong acid. Our second one, weak acid, it's called ethanoic acid, very popular as well. Students who have studied the topic of nomenclature, looking at the structures of these chemical compounds, if you want to challenge yourself a little bit further, see if you can draw out the chemical structure of ethanoic acid. Our next one, a weak alkali, ammonia, again very, very popular, used in any revision and any GCSE questions, looking at the dissociation of a weak alkali, ammonia. And finally, our strong alkali, sodium hydroxide, used in 99.9% of titrations that we're going to be looking at around the world. Very, very popular, strong alkali. Hopefully you're working through this together with me. You did this homework and you can reflect on your great work so far. Next thing to reflect on, this term of dissociation, the breaking down of compounds back into its elements or its ions. So before we continue this review to look at the dissociation of our strong and weak acid, weak alkali and our strong alkali, let's just have a look at what we were saying was happening in relation to this dissociation of our strong acids, our weak alkalis, our strong alkalis. We stated yesterday that a hydrochloric acid, or our strong acids in general, they were going to fully dissociate. Okay. Next, our weak acids and our weak alkalis, they were going to partially dissociate. Okay, so let's follow this here. Partially dissociate. And finally, our strong alkalis, similar to our strong acids, they were going to fully dissociate. We had our examples when placed in water. So your homework was to complete the 3 following my template of the first one when we placed our hydrochloric acid into our water. We can see here in relation to our definition, our hydrochloric acid, it is broken down into what we call its constituent elements or its ions. We have this separation taking place. We have fully dissociated when placed in water. Okay, our partial dissociation, we can see here with our ethanoic acid, we're identifying a reversible reaction is taking place. We're not having this full dissociation, and that is represented here with that reversible reaction. Same again with our weak alkali, our ammonia, we're having this partial dissociation. It can be reversed with a reversible reaction. We are not fully dissociated. And following this same template for a strong alkali, we have our sodium hydroxide dissociating when placed in our water, full dissociation back into its elements or ions. Perfect, okay? Thank you for your hard work on that. Part 2 of this chemical changes and this chemical analysis video that we're looking at is now going to incorporate a very popular practical piece of work within any chemistry lessons and a required practical within the GCSE course. We are looking at the topic of a titration. So it's very popular to be able to define what we actually mean by this titration. So a titration, please make a note of this, is where a solution of a known concentration is used to find the concentration of an unknown solution. If you want to just rewind and hear me say that again and pause it and make a note, please feel free to do so, because that definition is going to need to be understood in order to answer our past paper question that we will do as we get to it. Okay, so for any chemical analysis or chemical change calculations, we use in chemistry a very popular triangle. And this is going to help us calculate any titration calculations we need to do within our exam. Our triangle, N, C, and V. Similar to in your maths questions, we have our dividing by, if we're on top and below. If we're next to each other, we are multiplying. But what does N stand for? What does C stand for? And what does V stand for? Okay, so N, here we go, stands for the moles. Okay, just a unit of measurement in chemistry, not a small animal, moles. Next one, here we have, let's put it aside here, a bit more simple, C standing for the concentration. And our final one, V here standing for volume. Okay, so titrations, need to use our moles, concentration, volume, triangle, and in knowing that we will be able to answer many questions. A general golden rule that we always follow within chemistry when making these calculations, they say, if in doubt, calculate the number of moles. So if you are looking at a question, if you are wondering where to start, always calculate the number of moles from the data that we know. And to calculate the number of moles, we are doing that concentration multiplied by our volume. Okay, so before we get to our calculation, GCSE students, you have already done this titration. Year 9 students, already Key Stage 3 students, also watching this, you can prepare for future preparations in doing this practical by just working through this with me. So we have some quite technical pieces of equipment in doing this in order to perform this calculation back to our definition, where it's a technique where a solution of a known concentration is used to find a concentration of an unknown solution. Okay. 3 key pieces of equipment we are going to use. I hope you have this table down already. We are going to use our burettes. We are going to use a glass pipette, more accurate than the small plastic ones you may have used before. And finally, a conical flask. For people that have done this practical already, you know that we're placing our conical flask upon a white tile here, because within this neutralization reaction, using our indicator, which is in the conical flask, we are looking for this color change. And a white tile is a nice contrast to see this color change. Okay, so our burette, our pipette, and our conical flask, key terms that we relate to this. So what is the function of our burette? What is the function of our glass pipette? What is the function of our conical flask? So our burette, what does it do? It measures the amount, let me just move still. It measures the amount of acid, my table's a bit small, or alkali delivered into the conical flask. That's right, it's a little bit small so I can fit this into the conical flask. Okay. Next one that we want to be looking at, our glass pipette. It measures the amount of acid or alkali directly into our conical flask. So when we are setting up, we are using our pipette to measure the amount of either acid or alkali depending on which way you are working. Generally we have our acid within our burette. Generally in our conical flask to start with we have our alkali. So our glass pipette measured into the conical flask, our burette is going to deliver into. And finally our conical flask is holding either our neutralization reaction. Why is it a neutralization reaction? Because we're having an acid and an alkali reacting with each other. Okay, 3 key things, 3 functions we need to be able to identify. Let's bring all this together now using our triangle in order to calculate a quite technical question which is going to enable you to pick either 3 or 4 marks in your exam. Okay, so I would advise getting a calculator to perform this question. I've left mine over there, so I'm just going to collect my calculator. I'm still here. Still here. Locked in the school. You're locked at home. Alright. So, I've made a little space here for me to work in this area. Hopefully you can still see this triangle behind me so you can see exactly what I am doing. So, key pieces of information, let's have a look then. 28 centimetre cubed of sodium hydroxide was needed to neutralise 25 centimetre cubed of hydrochloric acid. It's giving us some nice information. The concentration of our sodium hydroxide was 0.400 moles per decimeter cubed. The first thing we would have noticed there were some different units. Different units is instantly ringing these alarm bells in our head when we're looking at this, thinking we're going to need to make some conversions within our calculation. Calculate the concentration of hydrochloric acid in moles per decimeter cubed. So we already anticipated that. We know that we're going to state that because we have already dissected this question. We've already identified what they want us to do. So calculate the concentration of hydrochloric acid in moles per decimeter cubed. Let's have a look at the triangle behind me there. Calculate the concentration of hydrochloric acid. So we need to get to a situation where we're doing moles divided by our volume. And let's go back to what we were saying before. If in doubt, calculate the number of moles. Okay, so let's see if we have enough room to work down here. That's going to be step number 1. Please work through this with me. I've not anticipated a lot of room here, so I might have to rub off as we go. Let's work methodically. Let's put everything in order. So the reason why I'm calculating my moles of sodium hydroxide so far is because they have given me 2 pieces of information about our sodium hydroxide. They've given me the volume, which is here, we have our volume measurement, and they've given us the concentration. Alrighty then, so we're happy with that. So let's dissect this information as we go. So our concentration is 0.400. We've got our volume, and we're going to multiply that by 28.0. But if you remember what I said before, we're in 2 different units of measurement with our volume here. We are in decimeter cubed and we are in centimeter cubed. So it is very important that we can convert between these volumes. Centimeter cubed to decimeter cubed. We are dividing by 1000 to get here. So we can put in our calculation by 1000. Probably want to use your brackets here, or you can break it down further. You can do your calculations, you can do your conversion first into decimeter cubed, and then you can multiply. Okay, so let's have a look. I'm going to do my conversion first, makes life a little bit easier. So let's convert it to decimeter cubed, 0.028, multiply by 0.400. Let's convert it, don't want a fraction. That's giving me 0.0. Wow, stretching now. 1, 1, 2. Okay, we did our conversion. Okay, so we were calculating there our moles per decimeter cubed. Wow, a lot of work so far. Okay, next step. Here is the nice little trick we can have here. Within any GCSE question, they're going to make it nice and simple. we say we are now in what we call a 1-to-1 molar ratio. So the information that we've taken from our sodium hydroxide, we can just bring it into our next step and use it for our information for our hydrochloric acid to calculate the concentration. So let's take it step by step. So we are calculating the concentration of hydrochloric acid. And to do that, we are going to take our information from moles of sodium hydroxide, so 0.0112 divided by, where are we now? Let's find a volume for our hydrochloric acid. Okay, here we go. So let's convert that, don't forget. 1, 2, 3. Zero point zero two five. 0.0112 divided by 0.025. What is our answer? So we are having 0.448 is our answer. About 3 marks so far. Let's refer this to our unit of measurement, moles per decimeter cubed. Great stuff there. So our concentration of hydrochloric acid, we did it using our moles divided by our volume, 1-to-1 ratio to get our answer. Yeah, let's keep that there. Let's give ourselves 4 marks within the exam. Nice and simple. Okay guys, thank you for watching. GCSE required practical along with a calculation template that will allow you to use this template to answer any question they're going to ask you. Always remember to convert into your decimeter cubed. Conversion divided by 1,000. We are in our volumes. Okay, thank you for watching.